Hello everyone, Mike with Spray Jones, and as mentioned, we're going to get into taking a look at how exactly resistance value is calculated and what bearing that is going to have on our insulation and our decisions that we're going to be making. And I think there is no greater topic than pulling the rug out from underneath this fallacy that has been put into the American and Canadian consumer. And it's not that initially anybody was trying to deceive us. It was that a test was developed to study one mechanism primarily of heat loss. And as a result, that has transformed an industry into thinking a certain way and behaving a certain way when it doesn't have all of the information to make its decisions. So before we get into it, I want to say thank you to everybody that has come on board and subscribed to this channel. It's my intent to continue to educate and inform you. I am unapologetically 100% a spray foam guy, and this is largely an apologist channel for the spray foam industry. Now, it's for my business. All right, I get paid to spray foam, and I get paid to do a good job. So I do take a look at other products, but I'm not reviewing products. So that's what we're here to discuss, and I'll show you as we get deeper and deeper into other products and how foam behaves as to why I'm so convinced that spray polyurethane foam insulation is as modern as tomorrow, and I don't think in my lifetime anything's going to come up that can top what it can do and why. So thank you for tuning in. Let's get into the information. This information I'm presenting is nothing new. There's a number of other good channels that have engineering and architectural information, and they go over in quite lengthy detail the R value test, and so I'm not saying anything new. All right, this has been already described before, and Belinda Carr on her architectural products channel does a very good job and very good video illustration of the R value test, but I'm going to put the Spray Jones sort of spin on it. So we are dealing with an ASTM C518 test that is conducted at 75 degrees Fahrenheit temperature. And to just cut to how this test is done, let's read what it says on this site here, the test procedure down here. This test uses a heat flow meter apparatus. The heat flow meter consists of a cold plate and a hot plate, which incorporate heat flux transducers for measuring heat flow. The material to be measured is placed between two plates, which are controlled to different temperatures to create a heat flow from hot to cold plate, which is measured by transducers. The device is calibrated against materials of known thermal conductivity and can be used to measure flat materials in wide range of thicknesses and conductivity. Tests are commonly performed with a mean temperature between 35 degrees Fahrenheit and 110 Fahrenheit, with the most common being 75 degrees Fahrenheit. A temperature difference of 40 degrees to 50 degrees Fahrenheit is commonly used. The end result, thermal conductivity or K value and thermal resistance, hence R value, are determined. These values can be used to determine energy losses through a material. This test can be used to satisfy R value regulations for insulation materials, such as the U.S. Federal Trade Commission's R value rule. All right, that is what the bulk of the test says. Now, let's discuss the history of this test and what exactly is going on. If you are going to measure heat loss through conductivity, now it needs to be noted here there's three types of heat loss, right? There is conductivity, there's convective, and there's radiant. So conductivity is heat loss through touching. So if you are going to set up a test in which you want to measure your insulation's ability to be conductive and hence resist, you're not going to want any interference with air movement, which is convection, or radiant values, right? Because that would skew the results. So you're going to measure 1/3 of the equation, if you can think of it that way, which is what the ASTM C518 test is doing. It's measuring 1/3 of a 3-part equation. The problem with that test is if you want your product to fare the best, you have to make sure that it's not going to have any markers that's going to throw it off. No air movement and no water movement. So the test would be set up that the box would be dry, which it is, 0 water, 0 humidity level, and 0 air movement. So are you starting to see that there's a problem? I mean, if we want to get a pure test on thermal conductivity and resistance value, we're doing the right thing. The problem is we're leaving out 2/3 of the equation in real life. So insider information. Everybody wants inside. I believe that you need to take a very good look at what they're trying to accomplish with the test, because there's some very important things that we need to note that's going to have a huge bearing on the decisions that we make. The first is that most samples going into the C518 test are going to be kept at a 1-inch value. Now, this is the little bit of the conspiracy theorist in me. The fibrous industry, when this test was developed, no input was brought in for other materials. Frankly, a lot of other materials weren't on the market. Fiberglass goes back all the way to 1932, and if you're going to be testing any combination of an open cell fibrous material, whether it's cellulose, mineral fiber, glass fiber, any type of fiber, hay, straw, newspapers, take your pick, you're going to want to minimize the amount of convective loop that you can get inside the material. So 1/2 inch is going to be too little, 1 inch sounds good, 2 and 3 inches is going to be too thick. If you actually take the insulation material in an open cell fibrous format beyond 1 inch, it doesn't fare as well, because you're going to get more convective loop within the material and it's going to throw out the results. So the optimal result to measure is going to be the 1-inch sample. So that's the first thing that skews our results. The second problem that we're going to run into is the fact that the test cannot begin until we reach steady state. Now, steady state is going to be defined as the insulation has reached saturation point and we're now getting a measurable loss, or the conductivity has reached from top to bottom and we actually have something coming out of the bottom to see. And I'll show you this chart that little diagram that I made. Steady state is easily illustrated by this diagram. The insulation has reached saturation point and has to have a measurable loss. So imagine you have a sponge sitting in your sink. You open up the tap at the top and start dripping, 1 drip at a time. You start dripping water. And the insulation is going to have to absorb the water. Now, for the purpose of this diagram, the water is our heat loss from hot at the top to cold at the bottom. So here's your energy flow. From high dissipation to low dissipation, right? So you're dripping. The sponge becomes saturated, and eventually we reach a point that for every drip that touches the top, 1 drip has to go out the bottom at the drain. We've now reached steady state. And this is when the test begins. There has to be a measurable loss so we can see how conductive our insulation is and how much resistance. If we're giving so much heat or an energy here, but only getting so much heat and energy out of the bottom, then we actually have something we can measure. But this data on how long it takes to reach steady state is vastly important, because if we have thermal mass ability in the insulation, we need to take that into account. And here's where the insider information comes in. What is the steady state rate? How long does it take till we hit steady state with this 1 inch of fiberglass that we put into the test, or 1 inch of mineral fiber, or 1 inch of cellulose? It doesn't matter, folks. Cellulose, mineral fiber, right? It's all the same. They take 4 hours at 1 inch that they can get a measurable loss. Well, what does it take to get through 1 inch of polyurethane foam or 1 inch of EPS? 22 hours. 22 hours minimum. So that's not factored into your insulation equation. So the test is, again, measuring no air movement, no moisture movement. We have a 1 inch sample so that the fibrous products fare the best as far as internal convective loops, throwing off and skewing the results. And the fourth point, we don't start the test until we reach steady state, and steady state data does not factor into our decision. We only want to measure what the loss value is once we start to get a loss value. So for expanded polystyrene and cork and any type of cellular plastic product that has some sort of a gas trapped in the cells, the data is going to be completely different as to how well it's actually working for an insulation because the test isn't set up to take any of that data into an account. So are you starting to see just how rigged this is? This has already moved our needle so far over that to base our decisions on this one test is really going to throw us off. So now we're going to get into studying a little bit more on this R value test, conductivity test, and getting into a lot more anecdotal evidence. But let's just pause for a minute and think about the 3 mechanisms of heat loss: conductive, convective, and radiant. So far, this test is only measuring one type. Think about a simple thing that we all have if we're driving a vehicle, a radiator in our car. Think about the fact that the radiator is using all 3 mechanisms of heat loss to cool down the coolant which is circulating through the engine block. You have got conductivity in the form of many, many, many pipes inside the radiator, which is maximizing the surface area, and then fins that go through those pipes to maximize surface area so that there can be maximum conductivity surface area. We then drive air through the radiator, which is convective, to pick up the radiating heat across the conductive surfaces to cool the entire and transfer the heat from high source to low source, which is going to be the air. The air and the radiant values are dissipating the heat, dissipating the energy. All 3 mechanisms of heat transfer or heat loss are working in a car's radiator. Now imagine, if you will, that we only would take into account conductive value. Imagine that we took the air out of your radiator. Everybody has had a vehicle at some point plug up or overheat that has had the rad plugged, right? That you've had dust, you've had dirt, you've had grime in the radiator, and you can't get enough airflow, or the fan quits, or the fan belt quits. Well, how is it that airflow all of a sudden in that radiator shuts you down? Well, massive amount of heat transfer due to the convection. And that's exactly where we're going now, is to understand what is happening in our buildings. So in 2000, Mr. David B. South wrote this absolutely skewing article where he skewered the fiberglass and the R value industry. Now, I'm picking on fibers, but you're kind of seeing that it's sort of the fibrous' test. It's not necessarily representing other products too well. And I'm just going to get in and read. We're not going to read all of this document. It's 11 pages long, but let's take a look a little bit what he says here. One of the fairy tales of our time is the R value. The R value is touted To the American consumer, to the point where it has taken a chiseled in stone status, the saddest part of the R fairy tale is the value itself is almost worthless. It is impossible to define an insulation with a single number. It is an imperative that we know more than a single R number. So why do we allow the R value fairy tale to be perpetuated? I don't know. I do know, if anybody knows. It obviously favors fiber insulation. Consider the R value of an insulation after it has been submerged in water or with a 20 mile per hour wind blowing through it. Obviously, the R value of fiber insulations would go to 0. Under the same conditions, the solid insulations would be largely unaffected. Again, R value numbers are funny numbers. They are meaningless unless we know other characteristics. Test to determine R value. We've taken a look at this. The test used to produce the K value is an ASTM test. The ASTM test was designed by a committee to give us measurement values that hopefully would be meaningful. A major part of the problem lies in the design of the test. The test favors the fiber insulations, fiberglass, rock wool, cellulose fiber. Very little input went into the test for the solid insulations such as foam, glass, cork, expanded polystyrene, and urethane foam. The test does not account for air movement, wind, or any amount of moisture, water vapor. In other words, the test used to create the R value is a test of non-real world conditions. Now, I've said it before, to be fair, if you want to test only for conductivity, the test is set up correctly. All right? That I will give them. But we just cannot allow that one test to factor into our energy codes. But it has. For instance, fiberglass is generally assigned an R value of approximately 3.5 for the inch. He's talking for the inch in the sample, which, by the way, an empty air cavity will achieve that. It will only achieve that R value if tested in an absolute zero wind and zero moisture movement. Zero wind and zero moisture movement are not real world. Our houses leak air, our buildings leak air, and they often leak water. Water vapor from the atmosphere, showers, cooking, breathing, etc. constantly moves back and forth through the walls and ceilings. If an attic is not properly ventilated, the water vapor from inside the house will very quickly semi-saturate the insulation above the ceiling. Even small amounts of moisture will cause a dramatic drop in fiber insulation's R values as much as 50% or more. Moving a little bit further down in his report here, we understand air penetration through the wall of a house. In some homes, when the wind blows, we often can feel it. But what most people, including many engineers, do not realize is that there are very serious convection currents that occur within the fiber insulations. These convection currents rotate vast amounts of air. The air currents are not fast enough to feel or even measure with any but the most sensitive instruments. Nevertheless, the air is constantly carrying heat from the underside of the pile of fibers to the top side, letting it escape. If we seal off the air movement, we generally seal in water vapor. The additional water often will condense. This now becomes a source of water for rotting of the structure. The water as a vapor or condensation will seriously decrease the insulation value, the R value. The only way to deal with a fiber insulation is to ventilate. But to ventilate means moving air, which also decreases the R value. This is going to be huge because the next set of 4 videos coming out is going to be all to do with ventilation, attics, cathedral ceilings, cathedral attics, and spray foam insulation, moving away from old-fashioned methods and what had to be to new methods and what can be and should be done. I want to say this with what he's just said. To the people that want to be putting fibrous insulation in front of spray foam, he's telling you right here that there are air currents not fast enough to feel or even measure, but with any of the most sensitive instruments. So, unless the wall cavity is being kept absolutely perfectly dry in the humidity of your home and no air movement within your house, how well do you think the bat insulation is performing that you put in a flash and bat situation in front of spray foam? I made a comment in one of the previous videos, that I said that the spray foam is carrying 90% of the weight. And this is where I'm getting these kinds of thoughts from, is that the fiber insulation is moving enough air through it to negate any of the resistance value that you think you're gaining in this test that we already can see is skewed. So if you think you're getting an R13 bat, I say you're not. I say you're going to be getting probably an R2, maybe 3 at best. And if you think there's no air movement, there absolutely is. Your home is charged with air. Air is flowing through the glass or the mineral fiber or the cellulose behind the sheetrock. It is flowing through. Now, it can't get past the foam, but it is flowing through the insulation. He's telling you right here, the air currents are not fast enough to feel or even measure with any but the most sensitive instruments. Nevertheless, the air is constantly carrying heat from the underside of the pile of fibers to the top side, letting it escape. Boom. Air movement through your insulation on the inside is negating its ability to do its job. Here's a good example that he gives of the attic insulation and the amount of cold, dense air and the warmer air flowing through. We saw this in the study that I showed earlier on Flash and Bat 2. I brought up the Oak Ridge National Labs attic study, where they started to see just how much cold air was flowing through the attic. Do you understand why attics are done with R40 and R50? It's to make up for this. It's to make up for the amount of cold, dense air that's going through the first 6 to 8 inches of loose fill or batted insulation. You're trying to put more and more insulation between you and the cold side to make up for the air leakage. Shocking. So we're seeing that air movement through our insulation and water movement through our insulation is hugely detrimental to the insulating ability. So here he states, the only commonly used solid insulation that absolutely protects itself from air infiltration is the spray-in-place polyurethane. When it is properly placed between 2 studs or against the concrete block wall or whatever, the bonding of the spray foam plus the expansion of the material in place will affect a total seal. This total seal is almost impossible to overestimate. In my opinion, most of the heat loss in the walls of a home have to do with the seal rather than the insulation. Then somebody already made a comment of this, waiting for this video to come out. They think that the air seal is almost more important than the R value. You are correct. In fact, most people cannot understand why we can blow the doors off heating loads with only 1 inch of foam. According to the R value test, we don't have hardly anything there. It's the air seal. For physical reasons, heat does not conduct horizontally nearly as well as it does vertically. Therefore, if there were no insulation in the walls of the homes, but an absolute airtight seal, there would not necessarily be a huge difference in the heating loss. This would not be the case if the insulation was missing from the ceiling. Air infiltration can most effectively be stopped with spray-in-place polyurethane. It is the only material properly applied that will fill in the corners, the cripples, the double studs, top and bottom plates, etc. The R value of the material is of no interest or consequence if air can get past it. Agreed. So, having absolutely no way of having your bat insulation airtight to the inside, not to the outside, in a flash and bat situation, you are throwing your money away. The polyurethane foam is what's providing the insulation and protection to your home. The bat insulation is just feel-good information. It's not really actually doing anything there. Okay, anecdotes. During the 1970s, my firm insulated a bunch of new homes in Snake River Valley of Idaho with 1.25, that's 1¼ inches of spray-in-place polyurethane foam in the walls. In 1970, the most popular number for the R value of 1 inch of urethane foam was 9.09. Do you know why that is? This is a blowing agent. Before the green environmentalists got a hold of us, we were able to put better chemicals in the product that were amazing insulators. It's only taken them 30 years to make us physically double the amount of material that we have to put into a wall to get the same as what we were getting 30 years ago. That's a whole nother subject. Using this value, we were putting an R of 1.25 times 9.09 equals 11.36 in the walls. This was much less than the R16 claimed by the fiberglass insulators. Today, using the charts from the ASHRAE book, we would only be able to claim an R value of the 1.25 inches of 7.5 to 9. That's total value, okay? So 1.25 inch, he could only claim somewhere between 7.5 to a total value of 9. Neither of these numbers make for very big R values. The reality is that people for whom we insulated their homes invariably would thank us for the savings in their heat bills. They would tell us their heating bill was half of their neighbors. They felt as if they saved the cost of the polyurethane foam in 1 or at most 2 years. This is anecdotal evidence, I know, but anecdotal evidence is also compelling and very real in our world. Most of these customers were savvy people. They would not have paid the extra to get the urethane insulation if it had not been better. So how is this possible? How is it possible that we are putting in an R7 or an R9 of spray polyurethane foam in a 2x4 wall, and the heating bills in the house that are receiving the R16 bat are half as much? Obviously, the R values are not equally. Obviously, the fiberglass is not giving us a true value. Back to my insulation innovation holds promise for true efficiency. So we've already seen this before. I showed this in the flash and bat video. If you want to check it out a little bit more, we're not going to read all of it. We're just going to scroll down here. Where the difference between the two structures, they built two identical houses, right? Another study is Canadian, conducted by Dr. Tony Shaw of Brock University in St. Catharines. He analyzed the energy consumption of two nearly identical homes built side by side to code standards. The difference between the two structures was the walls. One had 2x6 wall studs with R19 fiberglass bats. The other had wall structural insulated panels, or SIPs, rated to R17. So all right, we're underneath. We're R17 to R19. Under wintertime field conditions, the walls of the SIPS home delivered their exact rating of R17. The internal closed cell foam insulation in these panels isn't subject to air infiltration, so thermal performance remained high and consistent. The walls of the fiberglass insulated stud frame home, on the other hand, performed at an actual level of only R4. Because of the inevitable air movement within the hollow wall cavities. Hard to believe, but true. And then he goes on to say you can put all the building wrap, siding, and materials that you want on the outside of the house. The air still wafts through the wall cavities, carrying the energy with it. In the Brock study, the code-built home lost more than 60% energy than the SIPS panels. All right, what are we saying here? We are saying that the R values are not equal. We're seeing the information in the field. Now, I want you to understand something about the other part of the test, of the C518 test. It's a 1-inch sample, but it fits on all four sides. It fits perfectly into the box. It fits perfectly to the lower heat plate and the top plate. There's absolutely no gaps around it or on top of it. So that, again, is the fifth point of not realistic. Now, again, if you're just wanting a hyper-accurate test for thermal conductivity, we've got it. But don't take the conductivity test without convection, without radiant, without moisture movement, and then say that that's our total assessment for insulating values, right? Now, this favors the fiberglass industry, because they can claim that they've got R20, they can claim that they've got R30 and 40. The test is slanted. Our football team, the spray foam and the foam insulation of any kind, cellular, EPS, it doesn't matter. We show up and we've already got 20 points on the board. We have to overcome a 20-point deficit. What's the 20-point deficit? It takes 22 hours before we can start the test. It takes them 4. In the real world, that factors in. In the real world, the house cools down quicker. The house loses heat quicker. It gains heat quicker. It gains heat slower, right? 22 hours of thermal steady state matter. It matters huge, but it doesn't factor into these prescriptive results that the codes are going to be based on. So, water is going to affect how the insulation. You've got damp and wet insulation, either from a 60% 80% relative humidity outside, that's going to affect your insulation value. High humidity from the inside, that's going to affect your insulation value on open cell fibers. How it's fitted into the wall, fitted into the roof is going to factor in. How much air is traveling through it or not, and what temperature that air is. Because let's be honest now, here's the sixth point. Okay, air becomes much more conductive at super cold temperatures. And that's just physics, folks. That's because the air molecules are becoming closer together, because the air is becoming more dense. Therefore, the molecules come closer together. When they become closer together, the conductivity rises. So you actually become less insulative, or the conductivity goes higher and your resistance value goes lower when you get into extreme low temperatures. So we need an insulation that is not going to let air go through it, water go through it. We need it to be a tight fit to all four sides or six sides of whatever we're insulating. We need whatever insulation medium gas that we're using. If we're going to use air to insulate, well then okay. But if it's open and susceptible to the air changing humidity level or temperature, then the gas, the air, the oxygen, whatever we're using is going to be less conductive or more conductive. So if we truly want to be isolated, if we truly want to be insulated, we need to be bonded, we need to stop the air, we need to stop the water, and we need some sort of a gas trapped inside our medium material that isn't going to fluctuate and change its insulating value at extreme temperatures. Do you see where this is going? Do you see why I'm so biased towards polyurethane foam? Because only polyurethane foam fits into this the easiest. Now let's wrap things up. Okay, we're going to close with this. To recap, the problem with solely using the ASTM test as our insulation standard for measuring energy codes and insulation codes is following. 1, it's conducted at 75 degrees Fahrenheit with no air and no water incorporated into the test, which is fine for purity of a test, but not for real world. 2, starts when the insulation reaches steady state. That's not factored in. Therefore, spray foam is going to take 22 hours. Foam insulation is 22 hours. Fibrous only 4 hours. Therefore, the fibrous isn't doing as well as other insulations. 3, it measures conductivity as the primary purpose of the test. So out of 2 other mechanisms of heat loss, that's not being factored into our energy codes. 4, the sample in the ASTM test is usually done at 1 inches thick, no thicker and no thinner. That favors the fibrous industry the most. 5, the sample is a perfect fit on all 4 sides, actually 6 sides, top, bottom, left, right, front and back. 6, we know that air changes its thermal conductivity abilities based on high and low temperatures. It becomes much, much more conductive at low temperatures, and it changes its conductivity and effectiveness with up and down water levels. Those are 6 body blows to tell you that the ASTM R-value test is basically useless as an insulation gauge for thermal effectiveness. And I will not tolerate R-value discussions with somebody long term when we're choosing what we're going to do with spray foam. And codes have to change. Except I'm going to say this. We are fighting a multi-billion-dollar industry in the fibers that is going to have to be forced to change its ways because they are going to lose market share and stock price. The day that these codes are changed to reflect something other than pure R value, we've won and they've lost, and they know it. So they are going to fight us tooth and nail. All right, closing with this picture. All right, what are we seeing here? This was done by a friend of mine that ran a co-op home center. And he constructed this box because he sells rigid extruded polystyrene, foil reflective bubble wrap, and this was all the rage for a while. This was a foil-backed product called P2000. This is a expanded polystyrene, and every one of these products claims a different R value. So the extruded polystyrene is at 1.5 inches thickness here, claiming R10. The foil reflective is claiming somewhere around an R9. And the P2000, I think at this time they were claiming the outlandish R19 value at somewhere around the 5/8 thick with the foil face. Now what he's done is he's put a dual pane window, he's insulated each of the boxes, and then he's put a common light bulb, decorative light bulb in each and every one of them. It's the same light bulb. I don't know, 30, 40 watts maybe at each one. Now, you can see this is outside of his store. So whatever the ambient temperature is, you can see what the relative temperature inside the boxes were. Now, I'm trying to remember, and I think I'm accurate here, but I'm thinking that this day it was for sure around the -20 mark, the day he took this picture and sent it to me. So this is the setup that he's got. Let's see what the temperatures are in the box. That's -20 Celsius. So the extruded polystyrene is sitting at just under 25 degrees Celsius. And there you go, my American friends. There is your Fahrenheit on the left. And so it's faring extremely well on that cold day. Here is the EPS at 5/8 of an inch thick. It's foil face to the outside. And where this is 0 Celsius here, 32 on the Fahrenheit scale. So he's sitting 4 degrees Celsius, right? And again, this product's claiming like an R19. And then the foil reflective bubble wrap. I'll zoom in here and see if we can get just a little bit closer. Yeah, we're sitting maybe 11 degrees centigrade, well below the 60. We're in the 50s somewhere. And this is claiming the R9 on the foil reflectives. So I'm going to ask you, who's telling the truth? Who is actually giving the R10? And it's not hard to figure it out. It's the box on the left, the extruded polystyrene. And this is showing you how a closed cell foam. Well, yeah, let's talk about that. Let's talk about what these products are using. Here we have a extruded polystyrene that uses the most common blowing agent that they used to use was cyclopentane, which would be a derivative, a cousin of butane. And it would puff the mixture up and then force the mixture through like a Play-Doh type mold, like kids have for Play-Doh. And that's how it would extrude it and put that seam, that lip on the edge. The bubble wrap is air insulated in the little bubble packs. It's just CO2. And same thing with the expanded polystyrene. It's going to be carbon dioxide or steam blown EPS, which is just a simple plastic, so it's a steam blown. Now, each of these are performing fairly well given the outside climatic conditions, but only one is giving you true efficiency on the inside. And the point that we're trying to make with all of this is that our values do not perform the same for each product. Each of these products claims a different R value or similar R value, but have very different methods. So you want to use a closed cell product that has an inert gas trapped in the cells of the foam, and that is going to give you the true thermal performance with air movement, moisture movement, extreme highs, extreme lows, as you can see in this display. So I think we have proven, I mean, we could go on and on and on, but this video is long enough as it is, and there's probably only 2 people watching at this point. If you have, thank you very much. You're the 2 diehard fans. I can go on for a great length of time after this on more on the R values and compare BAT to foam, but I think the point has been made. The test is only measuring one type of real heat loss, and it's taking no account for other factors. And therefore, it cannot be used as the sole source decider in your insulation values. Yet, the codes are written that way. And what does that mean? It means right now we're in a headlock to try and wake an industry up, wake people up, and change some building codes. But we're going to be having to face a giant, so get your rock and your sling and get ready, because we're going to have to take down Goliath, which has been ruling this land for quite some time. So I'm going to cut it off here. Thank you for staying this long. Click the like and the subscribe and the share. I hope you like the Spray Jones way of doing things. And the next couple of videos now we're going to get into vaulted roof decks, everything to do with roofs. And if you've ever wanted to see vented, non-vented, shingle life, metal roofs, everything to do with it, that's where you're going to see this information. And the R-value stuff is going to be directly connected to it as we go into it in the next 4 videos. Thank you and have a good day.